Right, so I'm going to talk about ACC circuit lower bounds. Okay. So before I talk about what ACC is, let me first introduce the model of computation that we're going to talk about. So normally when we talk about an algorithm that's solving some problem, we have a fixed program and we run it on inputs that are arbitrarily long. So one program for all inputs. In non-uniform computation, we're allowed much more freedom. So we're allowed to have a separate program, A sub n, that's run on inputs of length n. So I get an input of length 1,000, and I have some logical circuit that has, say, 1,000 input wires here, and it prints out a single decision bit, yes or no. Okay, so I get some input of length 10,000, and I'll feed it to the A sub 10,000. Okay, so I get to design in advance a different logical circuit for each input size. Okay? And this is my program. This is my model of computation. So we say that poly size, or P/poly in the literature, is the class of problems which are solvable with a circuit family, so an infinite family of such circuits, where the number of gates in the nth circuit is a polynomial in n. Okay, so it's sum into the k. And a big open problem in complexity theory is to show that NP is not in poly size. So even if I allow you time to set up different circuits, say for the SAT problem, 1,000-bit instances of SAT, 10,000-bit instances of SAT, you still cannot solve them because the circuit will just be small. It will be polynomial size, and we don't think you can solve SAT in this way. Okay? So what would this sort of thing say? Well, non-uniform circuit lower bounds, in principle, they could lead us to proving specific numerical statements about the limits of computation. So one would expect from a proof that NP is not in poly size that we could say something like every logical circuit solving all SAT instances on, say, 10 to the 8 clauses requires at least 10 to the 60 gates. Okay? These numbers are totally made up, but one would expect from a proof that NP is not in poly size that we would be able to measure some trade-off between the size of this circuit, say for A sub 1,000, and 1,000. So there's should be some relationship between these two, and so if we get something like 10 to the 60, something which is larger than the size of the universe, then we would have some completely non-asymptotic statement about the difficulty of solving satisfiability. Okay. So that's one of the chief reasons why we'd like to prove lower bounds against this more powerful non-uniform model. So this is just repeating the definition for you. Now, most Boolean functions on, say, n bits, they require very large circuits. We've known this forever, since the theorem of Shannon, that with high probability, if you pick, say, a completely random function, then it will need a circuit of exponential in n size. Okay? But can we isolate such a function? Is there any interesting functions for which this is the case, which we can prove such a lower bound? So what sorts of algorithms, say where we have a single algorithm that's working on arbitrary input lengths, what sorts of algorithms can be simulated with polynomial size circuits? This is a very basic problem in complexity theory. The trouble with resolving this question in general is that non-uniformity can be very, very powerful. So there are certain formulations of the halting problem which can be solved using polynomial size circuits. So there are undecidable things which can be solved with poly-size circuits, so one has to be very careful. Sometimes unsolvable things can be solved with polynomial size. Let me move this thing. Okay. So in fact, it's open whether or not extremely huge classes, say nx, is contained in poly-size. So what does this mean? Well, nx stands for non-deterministic exponential time. So you thought NP was big. Nx is much, much bigger. Informally, what this question says is that can all problems with exponentially long solutions, verified in, say, exponential time, can they be solved with polynomial size circuit families? So the question seems obviously to be no, because, well, for one, exponentials are much, much bigger than polynomials. But other than this very simple intuition, we really don't know how to resolve such questions yet. And it's mainly because with poly-sci circuits, we can design a separate program for each input length. Okay, so what we can do is try to restrict the class of circuits that we're looking at, not just any logical circuit, but particular ones. And by restricting the class of circuit, we can make progress on understanding what can and can't be done. So in this talk, we'll talk about ACC circuits. So here we have a circuit family, so infinitely many C sub n. It has the following properties. So each C sub n, the nth circuit, takes n bits of input and outputs a bit, same as before. The gates of such a circuit, they can be AND, OR, NOT, or mod m. And they have unbounded fan-in, so they can take arbitrarily many inputs. And this mod m gate, for the purposes of this talk, you can think of m is equal to 6. Okay? That's already interesting. So mod 6 of, say, t input bits will be outputting 1 if and only if the sum of those bits is divisible by 6. Okay? So we just have some very rudimentary divisibility check as among the gates of our circuit. Now, the big restriction with these circuits is that they have constant depth. So there's only constant number of layers of gates from the input to the output. And that's something independent of n. And again, for the purposes of the talk, you can think of the depth is equal to 3. In the case depth 3 is already interesting. Mod m equals to 6, already interesting. Okay, so here's just some example of such a circuit. So here n is 11. There are 11 inputs. The size, number of gates, is 5. And the depth is 3. So there's 3 layers of circuits. And we can have different moduli here, but we have some, say, finite upper bound on the moduli. Let's say we have moduli no more than 6. Okay, so that's the basic definition. The big restriction is that we have a constant number of layers of gates to work with. So just some remarks about this definition. When I forget to tell you what the size of a circuit is, just think of it as polynomial in n. So it's, so this is going to be this ACC is going to be a subset of poly-size, so polynomial size circuits. And again, this is still a non-uniform model of computation, so it can compute some undecidable languages, which makes it interestingly powerful, but it also seems to be interestingly weak. So for example, ACC circuits can be efficiently simulated by constant layer neural networks. So we don't think those things can compute very much, but at the same time we get to pick a separate circuit for each input length, so that gives it some power. Okay. So where does ACC come from? Seems like a rather strange definition. So in order to understand it, we have to look a little bit about the history of where it came from. So sort of what was being done before we got to ACC. So what I'm going to present here is really a very, very brief history. It only gives some of the highlights. There's a lot more work that I unfortunately don't have the opportunity to talk about. But the basic idea behind circuit lower bounds was to try to prove that P is different from NP by proving that NP doesn't have poly-size circuits. So just trying to prove that NP is not in poly-size. And the idea was that we don't understand Turing machines. We don't understand algorithms. But I seem to understand AND, OR, and NOT. So let's try to understand circuits. So some connection of AND, ORs, and NOTs. So that should make it easier. So Itai, First, Sachs, and Sipser got the ball rolling in the early 80s, and they showed that the parity of n bits, so this is a very simple function, it can be an XOR, is not in AC0. The AC0 is just polynomial size ACC, but without the mod m. So it's a constant number of layers, but with only AND, OR, and NOT gates. So just having AND, OR, and NOT with constant layers, you cannot compute mod 2. That's what this says. So then it was natural to ask, well, what if I give you the mod 2 function for free? What if I throw in the mod 2 function as one of the gate bases, what can I prove then? Well, as Borofman-Smolinski showed, that you cannot compute the mod 3 function. Even if I give you the mod 2 function for free, and I give you and or not, and I give you constant number of layers. And in general, if you have P and Q, which are distinct primes, mod P can't be computed given sort of free access to mod Q in AC0. Okay, so then the next natural question was to say, well, what if I allow you mod 6? So what if I allow you something which is a mod, which is not a prime power and a composite? So mod 6. Suppose I allow you mod 2 and mod 3 for free. Then what can you do? So Barrington suggested this class ACC, and it was conjectured that the majority function on n bits, so computing the most popular bit, is not in ACC. So some time passed, and this conjecture remained open, and so then it was conjectured in the early 90s, okay, that the clique function is not solvable in ACC. Okay, so I give you depth 3, mod 6, or equivalently mod 3s and mod 2s, and ands and ors, show me that the clique function cannot be computed. Okay. This was in the early 90s, and so some time passed, and not much happened there. And so in the late 90s, someone said, okay, find me a function in non-deterministic exponential time that does not have ACC circuits. Okay. And very surprisingly, over the years, this question just ballooned to one of the most embarrassing open problems in complexity theory. And so the point of this talk is to reduce the embarrassment just a little bit and to at least establish the conjecture, this conjecture. The other ones remain open. So what do we prove? So our first theorem is the following. Let x to the np be the class of exponential time with an np oracle. So just slightly more precisely, we have a language L as an x to the np if and only if you have an exponential time algorithm A that has free oracle access to, say, the 3-SAT problem. So it can ask exponentially long 3-SAT queries, but it gets the answers in unit time, yes or no. So such an algorithm will recognize L. Okay, this is like an enormous class, but even interesting lower bounds, circuit lower bounds for this class remain open, more or less. So our first theorem is that there's a problem Q in x to the np, such that for every depth d and every modulus m, there's an epsilon so that Q doesn't have ACC circuits with mod m gates, depth d, and size 2 to the n of the epsilon. So we get exponential size lower bounds for x to the np. Okay. Now, just to remark, it's been known for more than 30 years that if you make this class a bit more complicated and make it x to the np to the np, or x to the sigma 2p, then, okay, you can directly construct by diagonalization a function that's designed to not have polynomial size or even so-exponential size circuits. Okay. But lowering the complexity of this thing, even by a slight amount, seems very hard. So that's theorem 1. Now, theorem 2 deals with this class NX. So, again, a language is an NX if there's a polynomial time algorithm A that, given exponentially long solutions to yes instances, will be able to verify them. Okay? Slightly more formally, L is in NX if there's one of these polynomial time algorithms A, so that for all strings x, x is in L, if and only if there's an exponentially long y, such that when we feed y to this verifier along with x, it will output 1. Okay, so this is exactly like the definition of MP, except we replace this polynomial here with an exponential. Right, so really, really long solutions. Okay. So our second theorem is that there's a problem Q in an X, such that Q doesn't have quasi-polynomial size ACC circuits of any constant depth. So you pick any constant depth that you want, and any polynomial that you want, and I will prove to you that this problem Q doesn't have circuits of that size and that depth. Okay, so that's the second theorem that we've proven. Just to remark where the boundary lies, again, it was known for more than 30 years that if you give NX access to an NP oracle, so it gets yes or no answers to the 3-SAT, that doesn't have unrestricted polynomial size circuits. And there was slight improvement over this, but nothing close to NX. Okay, so somehow these theorems are using the structure of ACC in a way that just the usual diagonalization over all possible circuits doesn't. So how do we prove it? The basic idea is to find some property of ACC that NX doesn't have. Okay, that's what we'd like to do, and somehow turn this intuition, this property that we find, into a proof. Okay, so we'd like to see what is it about NX that makes it hard, and what is it about ACC that makes it easy. So we can try to draw some intuition from the non-deterministic time hierarchy theorem. And basically what this says is all time hierarchy theorems do is that as you increase the amount of time that you allow to solve problems, there's strictly more problems that you can solve. So if you have a function little t and big T, such that little t grows more slowly than big T, then I can always find some function solvable in big T, non-deterministically, time that can't be solved in little t time, non-deterministically. Okay. So just a corollary of this thing is that there are problems solvable in 2 to the n time non-deterministically that can't be solved non-deterministically in, say, 2 to the n over n. Okay. So these problems are hard even to solve, say, 2 to the n over n time. Okay. So one question we can try to ask is, can some problem recognized by ACC circuits be non-deterministically solved somehow in less than 2 to the n time? So this question is terribly ill-formed because what does this really even mean? ACC is a non-uniform class, so it's impossible to simulate one of these things by even a Turing machine in general, because you can design a separate circuit for each input. So the program size, in a sense, is infinite. So we can't solve this question directly, but we can try to latch onto some property of ACC that's different, makes it different from, say, an arbitrary black box, and use this particular property to prove a lower bound. So the property that we're going to look at is that of determining satisfiability of ACC circuits. So in general, let C be some class of Boolean circuits. So it could be the class of all Boolean formulas. It could be CNFs, ANDs of ORs, or it could be ACC circuits. For every such class, we have a CSAT problem, which is, given a circuit K from this class, determine whether or not it's satisfiable. Is there an assignment to its inputs so that the circuit prints 1? Okay. Now, this problem is NP complete for essentially all interesting circuit classes C, including CNF. And if we just try all possible inputs, all possible 2 to the n inputs, and stick them in and evaluate, we can solve the CSAT problem using exhaustive search, of course. Okay. The question is, can we do a little bit better than this? Can we improve on this by a slight amount? And if so, what would that mean? Okay. So the main message of our result is that improving on exhaustive search for this CSAT problem, even by a tiny amount, will already imply circuit lower bounds against the same class of circuits solving NX problems. Okay? To put this in pictures, suppose this is some example circuit from my class. It has n inputs and it has polynomial size. Suppose I can inspect this circuit somehow and figure out whether it has an input, which makes it print 1. And I can do this not in 2 to the n times into the c time, but something slightly faster, like 2 to the n over n to the 10. Here 10 is a substitute for some sufficiently large constant. Say n to the 4 will do. The main point is that this running time is independent of the c. So for all polynomial sizes, I'm getting some improvement over exhaustive search by some polynomial amount. Okay? So it seems like a very, very minor thing, but in fact, such an algorithm can be used to prove for the same class of circuits that they cannot solve problems in NXP. So I can construct an explicit function in NXP that cannot be simulated with these circuits using the fact that I have a slightly faster than exhaustive search algorithm for CSAT. Okay? So we're turning positives and negatives. We're taking algorithms and we're turning them into lower bounds. So you might wonder, like, why on earth might something like this be true? Like, how can we take a positive and turn it into a negative? Well, there's sort of two ways of looking at it. One way is that a faster CSAT algorithm is uncovering a weakness in representing computations with C circuits. So the fact that I can solve this faster than just trying all possible inputs means that the C circuit can't hide an input which prints 1, or which makes it output 1 from me. Somehow I'm understanding the structure of the circuit in a way that I don't understand with a black box. Okay? So somehow this says that C circuits are weak. Another way of looking at it is that this faster CSAT algorithm is uncovering a strength in improved exponential algorithms which run faster than 2 to the n. So I'm showing you that there's some problem which can be solved faster than 2 to the n that you didn't think could be solved, namely finding an input which makes the circuit print 1. So I'm showing that less than exponential time is somewhat strong and C circuits are somewhat weak, and somehow the algorithm is beating the circuit, and I'm going to try to use this to prove an explicit circuit lower bound. So have some NXP algorithm that doesn't have these circuits. Okay. That's the high-level intuition. Okay. So I'll just outline how the proofs really go. So first, we want to show that faster ACC SAT algorithms imply ACC circuit lower bounds. And in fact, the proof that we'll have will work for essentially any reasonable circuit class C. So designing faster SAT algorithms for arbitrary poly-size circuits imply arbitrary poly-size circuit lower bounds. And then the second step is to just design these fast SAT algorithms explicitly. Okay, and this is something unconditional. So it's a mixture of just algorithm design and complexity theory. So in a previous work, we showed that such a connection holds, that faster SAT algorithms imply lower bounds, but for only really polynomial size circuits. So we showed that if circuit SAT with n inputs and super polynomial size can be solved in slightly less than 2 to the n time, then we can prove that NXP is an n-poly size. And the idea there, which we'll use here, is to show that if we had both a faster SAT algorithm and that NXP is n-poly size, then we'll contradict this non-deterministic time hierarchy theorem that I stated earlier. We'll be able to design a generic simulation of every 2 to the n non-deterministic algorithm that runs in faster than 2 to the n, which is a contradiction because we know that as you increase the amount of time you have to solve problems, there are going to be more problems that you can't solve before. Okay? So we're going to take these two positive assumptions, two algorithmic assumptions, and derive a contradiction from them. Therefore, the SAT algorithm must imply a circuit lower bound. Okay. That's the idea. Okay, so just to give an example of the kind of theorem we can show here, so we can show, for example, that if ACC SAT with n inputs and, say, sub-exponential size, here epsilon is sufficiently small, if that can be solved in slightly less than 2 to the n time, then we get exponential lower bounds for x to the np. So x to the np doesn't have sub-exponential size ACC circuits. Okay? And in terms of designing faster ACC SAT algorithms, we can show the following. So for every depth d and every modulus m, there's some epsilon, so that ACC SAT with n inputs, depth d circuits with mod m gates, and 2 to the n of the epsilon size, that SAT problem can be solved in 2 to the n minus omega into the epsilon time. So here we're beating exhaustive search in the denominator by 2 to the n of the epsilon. So that's more than enough to get the lower bound here, to make this hypothesis hold and make the lower bound hold. Okay. So that's the kind of theorems we can show. Okay. So just an outline for the rest of the talk. So I'll show you first how faster SAT algorithms can be used to get lower bounds. Okay, this will take most of the time, provided I have enough time at all. So then I'm going to show, say more quickly, that we have faster ACC SAT algorithms. Just go over the ideas of how that works. Then, if I have time, I'll talk about how we get lower bounds for nexp. So you can take the proof of this theorem and make a few tweaks and get lower bounds for nexp. And then I'll talk about future work, so where this work is headed. Okay. So how can we prove that faster SAT algorithms for a circuit class imply circuit lower bounds? Okay, this is, again, the theorem that we want to show. And the proof idea, again, is to show that if we have a faster SAT algorithm, and we assume that x to the np has sub-exponential size circuits, then we're going to derive a contradiction to the non-deterministic time hierarchy. Okay. And we're going to use a specific property of non-deterministic exponential time. So we're going to work with a compressed version of the 3-set problem that happens to be nexp complete. And in this compressed version of 3-set, we're going to encode exponentially long 3CNF formulas with polynomial size circuits. So this is, again, the theorem that we want to show. So the particular problem that we use is succinct 3-set. So in the succinct 3-set problem, I don't give you a formula directly. I give you a formula implicitly. I give you a circuit, C, and then I say let F be the string that you get when you evaluate C on all of its possible assignments, say in lexicographical order. Okay? So let F be the truth table of the function computed by the circuit. Now I ask, is this formula F, so is this string F that you get, is it a satisfiable 3CNF formula under some natural encoding of formulas? Okay? So here I'm giving you a formula, but only implicitly. It could be just a poly-size circuit, but I'm sort of decompressing that into some exponentially long formula. And that asks, is this formula satisfiable? Okay. So it's well known that this problem is nx complete. So it's not too hard to see that it is an nexp. The idea is if you're given such a circuit, you just evaluate it on all possible assignments. They're exponentially many. You get some string. It's exponentially long. And you just treat it as a 3-set instance, and you try to solve it. So you try to guess a satisfying assignment for it and try to verify that. Okay. So this will be an exponentially long solution, which you verify. Okay. So this problem is an nx. And it's very nx complete. So in fact, for every language in n time 2 to the n, we have a polynomial time reduction from that language to succinct 3-set with the following properties. So x is in the language if and only if the output of the reduction is in fact a circuit encoding a satisfiable 3CNF. So the reduction does what it's supposed to do. The circuit will have polynomial size because it's a polynomial time reduction. But the most important property is that the number of inputs to this circuit, so here n is the length of the input x, this C sub x will have at most n plus 4 log n inputs. So the number of inputs relative to x increases by a very small amount. Okay? So these two properties you can get without much problem. But getting this property is much more difficult, but it's actually critical for our proof. So this is the first lemma that we use, and it's about just a structural property about the completeness of succinct 3-set. So the next kind of property that we want to have is that suppose I have one of these circuits encoding a very big 3CNF formula that's satisfiable. Does this formula have a satisfying assignment which is also compressible? So we say that succinct 3-SAT has ACC satisfying assignments if for every circuit that's encoding one of these exponentially long formulas, there's an ACC circuit of sub-exponential size that encodes a satisfying assignment to this formula. Okay? So by this I mean that if you evaluate this circuit D on all of its possible assignments, that exponentially long string represents a satisfying assignment to the original formula. Okay? So this property is just saying that compressible formulas, so those satisfiable formulas which are compressible, have compressible satisfying assignments. So there's some satisfying assignment to them which can be represented with a very small polynomial or sub-exponential size circuit. Okay? So the second lemma we'll use is that if we were to assume that x to the np had sub-exponential size circuits, then succinct 3-SAT does have ACC satisfying assignments. So compressible formulas will have compressible satisfying assignments too. Okay, so that's the second lemma. Should I talk about the proof? Well, okay, let me just give you a sketch of the proof. So the following can be computed in x to the np. The idea is you're given one of these circuits, it's encoding a 3CNF. What you do is you just evaluate it on all possible assignments. You get some 2 to the n linked string. Okay, it's some formula f. Then you use the NP oracle to find, say, the lexicographically first satisfying assignment to this very long formula. And then if your input is I, you output the ith bit of this formula. Okay? This is something that you can do in x to the np by just making a bunch of oracle calls to SAT and finding the first assignment that satisfies it. But by assumption, we're assuming that x to the np has sub-exponential size ACC circuits, so this procedure can be implemented with an ACC circuit of sub-exponential size. So by just sort of sticking in the circuit C as input, by evaluating the thing over all possible I, we'll get a satisfying assignment. Okay? So if this huge complexity class has sub-exponential size ACC circuits, then succinct 3-SAT will have ACC satisfying assignments. Okay, so these are the two lemmas that we're going to use. Okay, so first I'll give you one attempt at the proof. It will break, and then I'll talk about how to fix it. Okay, so the basic idea is to assume the opposite, right? So we assume that we have a faster ACC-SAT algorithm, and we assume that x to the np has sub-exponential size ACC circuits. Okay, so and let L be some arbitrary language in n times 2 to the n, and we want to produce a faster algorithm for L no matter what L is. Okay. Now, by lemma 1, we have this very nice reduction from L to succinct 3-SAT, no matter what L is. So, given an input x, let C sub x be the circuit generated by this reduction, and let phi sub x be the exponentially long formula that you get when you evaluate C sub x on all possible assignments. Okay? Now, by lemma 2, succinct 3-SAT has sub-exponential size ACC circuits encoding a satisfying assignment to phi sub x when it exists. So there's some ACC circuit y of sub-exponential size, so that as I evaluate this circuit y on all possible I, it will output the ith bit of a satisfying assignment for phi sub x. Okay? So I have a formula, a 3CNF formula, phi sub x, represented by a small circuit. I have a satisfying assignment, presumably y, and it's represented by a small circuit. So with these two compressed representations, I'm going to show you how to use a circuit SAT algorithm to solve L faster than 2 to the n. Okay, and here's the basic idea. So given an input x of length n, we non-deterministically guess some ACC circuit y of sub-exponential size. Okay? And presumably, this is supposed to encode a satisfying assignment to this phi sub x, this implicitly encoded 3CNF formula. So this thing's supposed to encode a satisfying assignment. Okay, so we'll just guess it, and we'll try to check that it actually does encode such a thing. Okay, so we'll construct the circuit D, which also has sub-exponential size, and it has the following outline. So the inputs to the circuit will feed directly into this C sub x. So this is the circuit which is generating the clauses of phi sub x. Okay, so I will feed this thing n plus 4 log n input bits, say some I. And by stringing together copies of C sub x, I will make it output, say, the ith clause of this very large phi sub x, which is satisfiable if and only if x is in the language. So for this arbitrary language L. Okay, so I have this circuit, and it's printing arbitrary clauses for me, the ith clause, when I give it I. So what does it print? So given an I, it will print some variable index A, and it'll print a sign bit for it. Another variable index B, another sign bit, so whether or not that variable is negated in the clause. And another variable index C and another sign bit. Is this variable negated or not? Okay, so this just printing the information for the ith clause of this formula, given I. Okay? Well, we want to verify that this ACC circuit Y we guessed is actually a satisfying assignment. So what we do, we just feed these indices A, B, and C into Y. Because Y is supposed to give us, if we give it A, the right bit to set A to so that we satisfy the whole formula. Okay? So we feed A into Y, B into Y, C into Y. So we have these 3 copies. And what we get back are 6 different bits. Right? We get sign bits, and we get presumed satisfying assignment for each of the 3 different variables. Okay? So this thing is outputting assignments to these 3 different variables. So then, using a constant size circuit, we can just take these 6 bits, mash them together, take the ORs of the appropriate things, and this circuit will output 1 if and only if the assignment encoded by Y does not satisfy the ith clause of phi sub x. So we make it output 1 if it does not satisfy. And the reason why is that suppose this circuit's unsatisfiable. Okay? That means that every I makes the circuit output 0. Okay? That means that for all I, the assignment encoded by Y satisfies the ith clause of phi sub x. This means that Y satisfies all the clauses of the formula. Okay? Well, that's exactly the same as checking that Y is in fact encoding a satisfying assignment to the formula. All the clauses are being satisfied. Okay. So it seems that if we just use our ACC-SAT algorithm, we can determine satisfiability of this circuit D in less than 2 to the n time. Because we guessed an ACC-Y here. But there's a big problem. And the big problem is that this circuit, which is the output of the succinct 3-sat reduction, it may not be an ACC circuit. And in fact, we don't believe that we could get ACC circuits, which are actually encoding exponentially long 3CNFs in this way. So that means that this entire circuit is not ACC, because even the small part of it isn't. So this is a big problem, and there is a way to get around it. And I'm not sure I can tell you even a bit of the details, but here's at least the lemma that we prove. So the lemma is that if P, polynomial time, has sub-exponential size ACC circuits, and we have a faster ACC-SAT algorithm, then we have a non-deterministic algorithm with the following very interesting property. If I give it a circuit C, which has size S of n, it will print an ACC circuit C prime of size roughly the same as S of n, which is equivalent to C. So it's taking an arbitrary circuit, N, and it's printing an ACC circuit equivalent to it coming out. And just under these two assumptions, so having a slightly faster ACC-SAT algorithm and assuming that polynomial time has ACC circuits. And I guess I should say what it means for a non-deterministic algorithm to print something. So what I mean is that on every possible branch of the non-deterministic algorithm, it either says reject or it prints one of these ACC circuit C prime, which is equivalent. And on at least one branch, it prints such a C prime. Okay? So this is sort of a very technical thing. And the idea is that you guess a few more circuits, helper circuits, which are going to help you verify that some C prime that you've guessed is equivalent to the circuit C, which is given as input. But I don't have time to talk about it. Okay. So what I want to talk about now is some faster ACC-SAT algorithms. How do we do it? Okay. So that has two ingredients to it. This is something completely unconditional and can be considered independently of the rest of the talk. So what we use is, one, a known representation of ACC that was known for a very long time. And it's a decomposition theorem. So it says that every ACC function can be expressed as a G of H's, where H is a sparse multilinear polynomial. And as I evaluate it on all assignments, 0, 1, all 0, 1 assignments, I get some number between 0 and k, where k is not too large. It's quasi-polynomial in whatever circuit is implementing this function. And the function g, it takes something between 0 and k, and it outputs a single bit. And it can be some arbitrary function, just can be seen as a lookup table. Okay? So in a sense, we're decomposing f into a multilinear polynomial and a short lookup table, quasi-polynomial lookup table. Okay? So we combine that with a fast Fourier transform for multilinear polynomials. And basically it says that given a multilinear polynomial, h and its coefficient representation, so just tell you what all the coefficients of the monomials are, then we can compute the value of this polynomial on all 2 to the n points in the Boolean hypercube in polynomial amortized time per assignment. And the big gain here is that this could have 2 to the n coefficients. So the naive algorithm would take 4 to the n, because for each possible point, you could, in principle, take 2 to the n time to evaluate the polynomial on figure out all the different monomial values. But in fact, it's well known that you can get 2 to the n times poly n time. Okay. All right. So I'm just going to skip to a picture proof of how the ACC-SAT algorithm goes, and then I'll conclude. So we start over here with a circuit C. It's an ACC circuit, and it has sub-exponential size. So just think of epsilon as sufficiently small. Okay. So we first do an input size trade-off in the circuit. So we just take the first n of the epsilon inputs of the circuit, try all possible assignments to them. Each assignment induces some new copy of the circuit. We take the OR of all these copies. Okay, so we get some circuit which is slightly larger, but it has fewer inputs than before, because each of these different copies has into the epsilon inputs plugged in. Okay? So this circuit is satisfiable if and only if this circuit is satisfiable, and the depth is increased by only 1. Okay? Then we apply this decomposition theorem so that we decompose it into a G of H's. So this is a multilinear polynomial, and this is some lookup table. And then, using an f of t, we evaluate this multilinear polynomial on all of its possible assignments, but there are only 2 to the n minus n to the epsilon assignments in polynomial amortized time per assignment. So the point is that we reduce the number of variables here to n minus n to the epsilon, and that gives us some gain. And once we have all the values of the polynomial, we can just look up if there's anything there which is going to make G print 1. Okay? And that's just at a very high level how the algorithm goes. All right. So how much time do I have? Negative 3 minutes or something? Yeah, okay. So, all right, so let me go to future work. So there are sort of 2 obvious directions. One is to replace this huge class NX with simpler complexity classes. And naturally, SAT is in a sense, it's a very trivial circuit property. You're checking whether a circuit is all zeros or not. So we may need to prove on exhaustive search for more complicated properties than just that. Another direction is to replace ACC with stronger circuits. And what this work shows is that in order to do that, it suffices to design faster SAT algorithms for, say, Boolean formulas or polynomial size circuits. You get a slightly faster SAT algorithm, you will get NX lower bounds. Okay? In fact, using the variants of the PCP theorem, we can weaken the hypotheses. You don't have to solve SAT directly. You can even solve a certain type of de-randomization problem, and that would also work. Okay. Another question that I think can be proved using these techniques is to show the uniform version of ACC, where you have a uniform algorithm generating the nth circuit for you, is different from NP. So I think we can scale this stuff down. And finally, in general, what we showed here is that circuit analysis algorithms can be used to prove circuit lower bounds. Can we go in the opposite direction? And so what other connections are there? So in general, I would like to encourage people to try to find more connections between algorithms and lower bounds. Thank you.